momentum thickness. So in this momentum thickness, boundary layer first, so without plate, and second one with the plate. So in our previous video, so we have seen displacement thickness, right? So displacement thickness also we have seen like this, no plate, right? Here there is a plate, right? So without plate, flow will be like this, because in velocity there is no change, right? So when you place a plate, your velocity will be looking like this. So velocity will be getting zero at surface of the plate and gradually increasing. At some point of time it reaches the free stream velocity, right? So first of all, what is momentum? So momentum is nothing but mass into velocity. So symbol we can give theta, right? Mass into velocity. So here the velocity is capital U, but here the velocity is small u, because the velocity is changing with respect to y, right? So let us take a small section in first case without plate, and second case also same we can repeat. For the small section we can give a vertical height dy. Here also the vertical height will be dy, right? So the horizontal dimension may be when the flow is happening along the plate, right? Or without plate also, right? Your fluid will be flowing when the fluid is flowing on the surface or the plate, it will be facing the fluid element will be facing the breadth of the surface or breadth of the plate, right? And also the height. The fluid element will be facing the breadth and height, right? So why we are discussing breadth and dy means, so here we are going to rewrite the mass like this: density into area into velocity into again velocity, because it is momentum, right? So here for the first case, velocity will be rho a small u into capital U. So this is the momentum for first case. And for second case, that is with the plate, where theta will be, right, momentum will be rho a small u, and velocity also will be small u, because here the velocity is u only, but here the free stream velocity will be capital U, right? So this is the difference between the momentum equation, right, with no plate and plate. If you have a plate, your momentum formula will be like this. If you are not having any restriction, right, that is no plate, means your momentum formula will be like this. So here also, as like as our previous thickness, displacement thickness, here also we are going to calculate the what is the amount of momentum decrease per second, that we are going to calculate, right? So this is without disturbance momentum, this is with disturbance momentum, right? So the difference will be, so the common term rho a into u, right? And within the bracket u minus u, capital U minus small u, these two difference, right? So this is about the decrease in moment. right? So if you want to calculate the so now we have calculated only for this amount, only for this dy. So here I have to add one more thing. Instead of area, um, rho into b into dy. So b into dy is nothing but your area, right, into u. So here itself you can replace the b into dy instead of a, and here also b into dy, because in both the cases we are taking the same kind of strip only, same kind of element only, same size of element only, right? So we can change the area like this, and we can write u, capital U minus u. So that is the momentum decrease. So here the momentum will be high because there is no restriction, right? Mass of the fluid and velocity of the fluid will be high here, because practically here there is no restriction, but here there is a restriction because here we are placing a plate. The restriction will be there, so the momentum will be getting reduced. So that difference only we are getting here, rho into b into dy into small u into u minus u. For the whole section, that is from the surface of the plate to where the fluid reaches the maximum velocity, that is mainstream free stream velocity, right? So that thickness is nothing but we know that there is boundary layer thickness. So if you want to calculate the momentum decrease for a whole section, here we are going to have a integral, limit will be 0 to del, right? And your rho b dy, that is area b into dy into small u into capital U minus u. So you can bring your dy at last, right? So finally you can write like this, rho b dy into capital U minus u, sorry, your dy can be here, and here you can put u, right? So this is our total momentum loss, total momentum loss per second, right? So I am going to, idea is by introducing a thickness, that is momentum thickness, we will be reducing the loss, momentum loss. So the momentum, how we are going to introduce the momentum thickness here, the boundary layer usually forms from the leading edge here, right? So now I am going to introduce some thickness, so the boundary layer getting displaced, boundary layer will move some height. So indirectly you can increase the height of the plate, or the formation of boundary layer starts here, right? Your boundary layer starts here. So if you do that, if you do like this, that means if you are increasing the plate thickness here, right, certain height theta is, so when you increase the thickness of the plate, right, so your loss will be getting reduced, momentum loss will be getting reduced, right? So that means mass into velocity is our momentum, rho, right? So your thickness, now we have a different thickness, not dy, sorry, height, b is same, right? So your thickness will be height will be theta, that is thickness, right? Here we were using dy, right? Here we were using dy, but here we are introducing height, right? So momentum thickness we are introducing either surface or plate. By introducing this thickness, by adding the thickness either in the surface or in the plate, so you can avoid the momentum loss, right? That means your boundary layer starts here only. So that means amount of flow, amount of fluid flow, and also velocity, right? Mass into velocity only our momentum, right? So that loss will be getting reduced. So theta, b into theta into your capital U only, right? So this is your mass, and velocity is will be equal to 0 to del, right? Rho b u into u minus u dy. So this is your total loss, right? So after introducing the thickness theta, so your momentum will be like this, right? So finally, so you can remove the common terms, rho b, here also rho b, right? Now you will have theta is equal to 0 to del, right? So when you bring this u to this side, so u by small u by capital U into capital U minus small u into dy, and finally, right, if you bring this capital U outside, if you bring this capital U outside, so your equation will be 0 to del into 1 minus small u by capital U into dy. So this is your momentum thickness, right? This is your momentum thickness. Thank you. So thank you. So this is, when you introduce this theta, so your momentum loss getting reduced. That is the idea behind the momentum thickness, to reduce the loss, momentum loss. Especially in displacement thickness, we were reducing the mass flow rate, right? We were reducing the mass flow rate by introducing the same kind of displacement thickness, del star. Here we are introducing the some thickness, that is momentum thickness, for reducing the momentum loss. Thank you.